So in this video, I want to look at the normal probability density function, and I want to discuss some common misconceptions that students have and try to help you to avoid them. So first of all, the equation of the normal probability density curve is this equation right here. Kind of an intimidating equation. So y equals 1 over sigma, the standard deviation, times the square root of 2 pi, pi being the normal pi, 3.14, 159, etc., times e. E, if you'll remember from college algebra, is approximately 2.718. That's the natural exponential function, raised to the negative 1/2 times the quantity, x minus mu, the mean, divided by sigma, the standard deviation, all squared. Now, if you look at the x minus mu over sigma, that should look familiar to you. That is a z-score. Okay? So this is the equation of a normal probability curve. Okay? So the misconception that I want to try to help you to avoid is that oftentimes students think that there's like one normal curve. Well, there's not. There's an infinite number of normal curves. As the values of sigma and mu change from problem to problem, we get a different normal curve. The curves all have the same basic look. They all share the properties that we discussed in the previous video, but there's an infinite number of normal curves. For example, suppose I have a normal curve with mu equals 50 and sigma equals 4. Okay? Then the probability density function for that normal curve with a mean of 50 and a standard deviation of 4 will be y equals 1 over 4 times the square root of 2 pi, putting 4 in for sigma, times e to the negative 1/2 times x minus 50, because that's the mean, divided by 4, because that's the standard deviation, squared. So let's take a look at that graph. So here I'm pulling in my graphing calculator, and I have typed this equation in to the graphing calculator. So, and I've set my window. I'm looking from 34 to 66 with a scale of 2, and I'm looking from 0 to 0.25 on the y with a scale of 1. If I graph this, this is this normal curve that has a mean of 50 and a standard deviation of 4. Now, what if I instead have a mean of 50 and a standard deviation of 2? Well, then our equation will be y equals 1 over 2 times the square root of 2 pi times e to the negative 1/2 times x minus 50 divided by 2 squared. So let's take a look at that graph. So I have now typed that equation in y2 in my calculator. And so if we look at the graph, notice that in this particular case we get a different normal curve. Notice that it is taller and skinnier than our original curve. That is because now the standard deviation is 2, which means this graph is less spread out than the original graph, the blue one that you can see here on my calculator screen. So the blue graph has a mean of 50 and a standard deviation of 4. The red graph has a mean of 50 and a standard deviation of 2. So the 50 is the center. Notice both graphs are centered above 50, but the red graph has a smaller standard deviation, which means it's less spread out. And so that means it has to be taller and skinnier than the other graph. Okay? Now, what if we have a third normal graph? What if we have a curve that has a mean of, say, let's say we have a mean of 40 with a standard deviation of 4. Then the equation of that normal curve is going to be y equals 1 over 4 times the square root of 2 pi, again 4 here because that's sigma, times e raised to the negative 1/2 times x minus 40 in this case because mu is 40 divided by 4 because that's the standard deviation squared. So let's take a look at what its graph will be. So I have typed that equation in my calculator. And so if we look at the graph, notice that this graph has the same shape as the original graph, except it's just been shifted over so that it's centered above 40 instead of being centered above 50. So again, that's the point. The point is that the mean and the standard deviation are the parameters of this graph. So as the mean and the standard deviation changes, the specifics of the graph changes. So the mean tells us where the graph is centered, and the standard deviation tells us how spread out it is. So the blue graph and the black graph here have the same standard deviation. Their spread's the same. They look exactly the same, except their means are different, so they're centered at different locations. And again, the red graph has the same mean as the blue graph, so they're both centered above 50, but the red graph is less spread out. I'm not going to do any other graphs, but if I created a graph that had a mean of 40 and a standard deviation of 2, then that graph would have the exact same shape as the red graph. It would just be over here centered at 40. So again, you don't have to really know this probability density function, but you do have to understand how the parameters mu and sigma affect the shape of the probability distribution.